Welcome to a cinematic journey deep within the human brain, where a microscopic battle for your wakefulness unfolds. Prepare to witness the inner workings of neuroscience, rendered in ultra-detailed 3D, as we explore the elegant mechanism that controls your alertness. We begin with a wide view of the neural landscape, a vast and intricate network mirroring the beauty and complexity of a distant galaxy. Our scientific camera movement is slow and deliberate, guiding us closer into the intricate biological terrain of the central nervous system. The transition begins now, moving from the macro-scale organization of the brain down to the microscopic level of cellular interaction. We plunge deep into the brain tissue, landing on an ultra-detailed 3D render of a neuron, the fundamental unit of communication. Observe the synapse, the critical junction where information is passed, a high-speed chemical messenger exchange fundamental to brain function. The stage is set for the main players. First, the molecule responsible for signaling natural fatigue, adenosine. As the day progresses, blue adenosine molecules accumulate, diffusing through the neural networks, preparing the brain for rest. Adenosine binds to specific receptors, acting like a brake on neural activity, gradually inducing feelings of sleepiness and fatigue. But here comes the antagonist, or perhaps the hero, depending on your perspective: caffeine. A rush of golden caffeine molecules enters the system, ready to interfere with the natural sleep-wake cycle. Volumetric lighting catches the shimmering gold of the caffeine molecules, highlighting their powerful intrusion into this microscopic domain. The confrontation is imminent. The two molecular messengers are about to compete for the same receptor sites. Caffeine is chemically similar enough to adenosine to fit into the receptor locks, effectively blocking the adenosine molecules from binding. By occupying these receptors, caffeine prevents the quote-quote brake from being applied, resulting in a noticeable surge of neural activity and alertness. With the battle decided, we see the results of this molecular intervention, a state of sustained wakefulness. The receptors are dominated by golden caffeine molecules, demonstrating the chemical basis for the feeling of heightened energy and focus. As we pull back to the cosmic neural landscape, it pulses with renewed vigor, a direct result of caffeine's stimulating presence. This microscopic battle illustrates the fascinating power of simple molecules to dramatically alter our perception and energy levels. Thank you for joining this futuristic visualization into the mechanism of wakefulness.
Usually when you brew your morning cup of coffee, you just think of it as this simple, comforting routine. You wake up, you pour the water, you drink the dark liquid, and you expect your brain to simply turn on.
Right, like a switch.
Exactly, like a binary switch. Asleep and then awake. But today, we want to invite you into a sort of theater of the mind, I guess, to show you what you're actually doing, which is consuming a highly sophisticated botanical weapon.
Yeah, it's entirely a functional illusion. I mean, we treat it like a warm hug for our nervous system, but from a biological perspective, you're initiating this massive systemic cascade of chemical interventions.
So we're going to visualize this for you on this deep dive. Picture a warm cup of coffee resting on, like, a minimal desk. Steam is rising slowly. Now imagine a camera zooming in, right? Pushing past the surface of that dark liquid down into the molecular level where the coffee actually dissolves.
Yeah, getting right down to the microscopic scale.
Right, and as we get down there, you start to see these specific molecules. Let's visualize them glowing softly, almost like these little golden particles suspended in the dark.
And that cinematic visual is actually crucial for understanding the science we're unpacking today. Because those glowing particles, they aren't just floating aimlessly. They are a highly targeted delivery system.
For a psychoactive compound.
Exactly. They have a specific destination and, honestly, a specific enemy to fight once they get there.
Our mission for you today is to track those golden invaders. We're going to follow them from that minimal desk, down into your digestive tract, through the toll booths of your organs, across the heavily guarded borders of your brain, and, straight into your internal neural universe.
Mapping the hidden battle between alertness and fatigue.
Yeah, this microscopic war. And we're pulling from a massive stack of sources today. Everything from complex pharmacokinetic research on metabolic rates to intricate memory studies out of Johns Hopkins University, and even some truly mind-bending neurobiology papers on Parkinson's disease.
It's a lot of ground to cover.
It is. Okay, let's unpack this, and we're going to start way before the brewing process. Because to understand what this golden molecule is doing in your brain, you have to understand why it even exists on Earth in the first place.
Which means we have to look at the coffee bean itself. Though botanically speaking, It isn't a bean at all.
Right, it's a seed.
Yeah, it's the seed of the coffee plant. And just to give you a sense of scale, humanity consumes nearly 10 million tons of these seeds every single year.
10 million tons. That is wild.
It's staggering. And the vast majority of what we drink comes from just two cultivated species, which are Coffea arabica and Coffea canephora, which we commonly call Robusta.
And this is where the romance of that cozy morning cup takes a slightly dark turn, I think. Because those golden particles we're visualizing in nature, the plant didn't evolve them to give a sleepy human a gentle pick-me-up before a meeting.
No, absolutely not.
It evolved them to commit murder. I mean, they are a weapon.
It's a literal evolutionary arms race. Caffeine is a naturally occurring alkaloid. You find it in roughly 30 different plant species globally. But for the coffee plant specifically, it serves as a highly potent natural pesticide.
Pesticide?
Yeah. The plant actually uses its metabolic energy to synthesize this compound and push it out into its leaves and its seeds. So when predatory insects attempt to consume the plant, the caffeine molecule attacks their central nervous system.
So it paralyzes them.
It paralyzes them, yeah. And if they consume enough, it kills them outright.
It's chemical warfare. We're literally brewing a defense chemical every morning.
But the sources point out it doesn't even stop with insects, right? It's used against other plants too.
Yeah, that's a phenomenon known as allelopathy. It's fascinating. The developing coffee seedlings actually shed their leaves and deposit high levels of caffeine directly into the surrounding soil.
They're dumping it into the dirt.
Exactly. They do it specifically to poison the dirt, which inhibits the germination of any nearby competing seeds. It's like a botanical scorched earth policy. The coffee plant is securing all the local water, the sunlight, the nutrients for itself by just making the ground toxic to everything else.
It's a highly aggressive survival strategy. And what's interesting here is how the environment dictates the concentration of this chemical weapon. The Robusta species, true to its name, is a much hardier plant. It generally grows at lower altitudes than Arabica.
And lower altitudes mean warmer temperatures.
Right, warmer temperatures, which means a vastly higher population of predatory insects and competing vegetation.
So it just needs more ammo to survive.
Precisely. To survive in that harsher, much more competitive environment, the Robusta plant has evolved to pump out significantly more of this defense chemical. Robusta beans generally contain twice the caffeine of Arabica beans.
Wow, twice as much.
Yeah. But even beyond the species, beans harvested from the exact same bush can have wildly varying concentrations. It depends on soil quality, rainfall, and the specific insect threats that year.
Okay, so we take these toxic seeds, we harvest them, and then we subject them to intense heat. We roast them, which actually brings up a huge misconception I think we really need to clear up, because it completely changes how you might order your morning drink.
Oh, the roast level myth.
Yes, because a lot of people, and I mean myself included for a long time, assume that a dark, rich, oily, heavy espresso roast is just absolutely packed with those golden caffeine particles, right? Especially compared to like a light blonde roast.
Because it tastes stronger.
Right. It tastes so intense, so it must be stronger.
Yeah, the flavor profile of a dark roast is incredibly intense, which naturally leads to that assumption. You're tasting the heavy caramelization of the sugars and the presence of these volatile oils that have been pushed to the surface of the seed. But the reality of the caffeine content is the exact opposite of what your palate is telling you.
Because the roasting process itself is basically cooking the weapon out of the bean.
Right, exactly. Caffeine is a remarkably stable molecule, but it isn't impervious to extreme thermal degradation. When you roast coffee, you're subjecting the seeds to temperatures between like 370 and 540 degrees Fahrenheit.
That is hot.
Very hot. And the longer you apply that heat, pushing a light roast into a medium and a medium into a dark French or Italian roast, the more the caffeine molecule actually begins to sublimate.
Sublimate, so it's changing states.
Yes. It transitions from a solid state within the bean directly into a gas, and it's just carried away in the roasting exhaust. Therefore, a dark roast coffee contains slightly less caffeine than a lighter roast, assuming you measure them out perfectly by mass.
So the people ordering the light blonde roast to sort of take it easy are actually getting a heavier dose of the pesticide.
Ironically, yes.
But what if we want to take it completely out? Like if we want the flavor of those caramelized sugars and the oils without the chemical weapon, how do we physically extract those golden particles to make decaf?
The decaffeination process is actually a marvel of industrial chemistry. Manufacturers extract the caffeine from the green, unroasted beans. So at this stage, the beans are essentially hard little rocks. The goal is to pull out the caffeine while preserving the hundreds of other volatile compounds that will eventually give the coffee its complex flavor once it's roasted.
Because they can't just boil them to death, obviously.
Right, you'd end up with decaffeinated cardboard.
Yum.
Yeah, not great. So they use highly selective solvents, and one of the most fascinating methods is supercritical carbon dioxide extraction.
Supercritical CO2. I mean, that sounds like something out of a rocket propulsion lab. What does that actually mean?
It's a state of matter. If you take standard carbon dioxide gas and you subject it to immense pressure and elevated temperature within a sealed stainless steel chamber, it enters this supercritical state. And in this state, it exhibits the properties of both a liquid and a gas simultaneously.
Wait, both at the same time?
Yeah. It can expand to fill the chamber like a gas, penetrating deep into the microscopic pores of the green coffee beans, but it also has the density of a liquid, which allows it to act as an incredibly efficient solvent.
So this liquid-gas hybrid pushes its way into the bean, grabs onto the golden caffeine particles, and just pulls them out without damaging the structural integrity of all the flavor compounds.
Yes. The supercritical CO2 is highly selective for the caffeine alkaloid. It binds to it, dissolves it, and then the pressure in the chamber is dropped.
And then what happens?
The CO2 reverts back to a normal gas. It just evaporates away entirely, leaving behind zero chemical residue on the beans. It successfully removes like 97 to 99% of the caffeine.
That's incredible, but they don't just throw those extracted golden particles away, right? It's not waste?
Oh, far from it. That recovered, naturally synthesized caffeine is a highly valuable, extremely pure commodity. It's gathered, refined into this white powder, and resold on the global market to pharmaceutical and beverage manufacturers.
So it's being recycled?
Totally. It becomes the active ingredient in soft drinks, energy drinks, over-the-counter alertness tablets. I mean, the caffeine in your afternoon diet soda very likely originated as a defense mechanism inside a coffee seed.
Wait, before we follow the cup into the body, I have to ask about tea. Because tea is the other massive global source of this compound. If I switch from a cup of coffee to a cup of black tea, am I getting a bigger dose of this defense chemical? Because I've often heard that tea leaves are actually more caffeinated than coffee beans.
Ah, you're touching on the great tea paradox. And it all comes down to the difference between dry weight and the final brewed volume.
Okay, break that down for me.
Sure. If you were to take a kilogram of raw dried tea leaves and a kilogram of roasted coffee beans, and you analyze them in a lab, the tea leaves do indeed contain a higher concentration of caffeine by dry weight.
So the tea plant is actually a more efficient manufacturer of the weapon.
It is. However, a typical serving of brewed tea delivers significantly less caffeine to your bloodstream than a cup of coffee.
Why is that if the leaves are stronger?
The reason is purely mechanical. When you brew tea, you are using a much smaller physical amount of the plant product. Just, 2 or 3 grams of delicate tea leaves suspended in a bag to flavor an entire cup of water.
Oh, whereas with coffee, I'm grinding up 20 or 30 grams of dense seeds and physically forcing water through them. So I'm using like 10 times the amount of plant matter to make the exact same size beverage.
Precisely. The extraction ratio is entirely different. The tea leaf itself is stronger, but the coffee beverage is much more heavily loaded with the compound.
Okay, so we've established what this molecule is and how it gets into our cup. The golden particles are suspended in that dark liquid on our minimal desk. You reach out, you take a sip, the liquid travels down your esophagus and splashes into your stomach. But from the sources, the stomach isn't really where the magic happens, is it? The real gateway into your internal universe is just beyond that.
Yeah, the stomach begins the process, certainly, but the primary site of absorption is the small intestine. And this is where your cinematic visualization really kicks into gear. The environment inside the small intestine is incredibly vast. It's lined with millions of tiny finger-like projections called villi.
Which maximize the surface area, right?
Exactly.
So imagine those golden particles just washing over this massive textured landscape. And within about 45 minutes of swallowing that sip of coffee, the caffeine doesn't even need to be digested in the traditional sense, does it?
Not really, no. It's rapidly absorbed right through the intestinal walls and distributed throughout all bodily tissues. It's incredibly efficient. Because of its molecular structure, it doesn't wait for complex breakdown processes. It just permeates the tissue and enters the circulatory system.
Let's visualize that circulatory system for a second. You have red blood cells flowing through veins and arteries like this vast, pulsing underground river. And now suddenly they're carrying millions of these glowing golden structures. The caffeine is racing rapidly through the bloodstream, being pushed by the beating of your heart to every single corner of your body.
And as they travel along this vascular highway, they eventually encounter the body's primary chemical processing plant, which acts as a metabolic toll booth. The liver.
Where's toll booth?
Right. The liver's job is to inspect what's in the blood and break down anything that shouldn't be there. And for caffeine, the liver utilizes a highly specific piece of machinery known as the cytochrome P450 oxidase enzyme system.
That's a mouthful, and I know from the sources we're looking at a very specific isozyme here, CYP1A2. But let's demystify that for the listener. What is an isozyme, and how is it actually interacting with our golden particles at this toll booth?
Think of CYP1A2 as a highly specialized molecular machine operating inside the liver cells. Its entire purpose is to grab hold of specific chemical structures, in this case, the caffeine molecule, and strip away certain parts of it.
Like dismantling a car.
Exactly like that. It breaks it down into smaller, water-soluble metabolites that your kidneys can then filter out into your urine.
So it's essentially dismantling the golden particles piece by piece.
Exactly. And we measure the efficiency of this dismantling process in terms of a biological half-life.
Okay, biological half-life.
That is the exact amount of time required for your liver to process and eliminate exactly 1/2 of the caffeine dose you ingested. For a normal, healthy adult, that baseline half-life is typically between 3 and 7 hours.
Okay, so if I drink a cup of coffee with 100 milligrams of caffeine at 8 a.m., by somewhere between 11:00 to 0 p.m., I still have 50 milligrams actively circulating in my blood, and then 25 milligrams a few hours after that.
That is the standard decay curve, yes.
Yeah, but the sources reveal that this 3 to 7 hour window is just a baseline, and it's a remarkably fragile one. The variables here are drastic. If we look at this liver toll booth, some outside factors act like a boss screaming at the factory to work faster, throwing the gates wide open, while others cause a massive catastrophic traffic jam. Let's look at smoking tobacco. How does cigarette smoke interact with a coffee habit?
Smoking has a profound and really immediate effect on this specific liver machinery. The chemical compounds in tobacco smoke, specifically polycyclic aromatic hydrocarbons, they enter the bloodstream and bind to receptors in the liver.
And what does that do?
It essentially sends a massive signal to the liver cells to manufacture more of the CYP1A2 enzyme. It's the process called enzyme induction.
So the smoke doesn't interact with the caffeine directly at all. The smoke tells the liver to build more toll booths.
Exactly. It puts the clearance system into overdrive. Studies show smoking increases caffeine clearance by up to 56%. Yeah. Consequently, the half-life of caffeine in an adult smoker drops dramatically by 30 to 50%. So a smoker processes those golden particles incredibly fast, which is why individuals who smoke often report needing significantly more coffee throughout the day to maintain the same level of alertness. Their liver is dismantling the drug almost as fast as they can drink it.
That makes so much sense. But then you look at a state like pregnancy, and the machine goes in the exact opposite direction.
Yes, pregnancy radically alters hepatic metabolism. As a woman's body undergoes these massive hormonal shifts, particularly with elevated levels of estrogen and progesterone, those hormones essentially compete for the liver's processing power.
They're taking up the lanes at the toll booth.
Exactly. So the ability to metabolize caffeine is significantly reduced, especially as she enters the 3rd trimester. The half-life of that single morning cup could be extended up to 15 hours.
15 hours, which means it's barely being cleared at all before the next day even begins. And it gets even more extreme when you look at the child itself, right?
Very extreme. Newborns and premature infants essentially lack this CYP1A2 enzyme entirely. Their livers are immature and just haven't started producing this specific molecular machine yet.
So how long does it take for them?
Well, for a newborn, the half-life of caffeine isn't measured in hours, it's measured in days. It ranges from 80 to over 100 hours.
Over 100 hours. That means if a newborn is exposed to caffeine, it takes over 4 days just to clear half of it.
Yes. It isn't until they're about 6 months old that their liver matures enough that their ability to metabolize caffeine matches or even exceeds adult rates. This is precisely why maternal caffeine intake during pregnancy and lactation is so carefully monitored by health authorities.
Because the baby simply does not have the infrastructure to clear the chemical. It just builds up in their tiny circulatory system.
Exactly.
Then there are the pharmaceutical interactions, which are arguably the most surprising part of the research we read. Oral contraceptives can extend the half-life by 40%, effectively doubling how long it stays in the system. But the most shocking interaction in the entire stack of research we reviewed is with an antidepressant medication called fluvoxamine. The data says it reduces caffeine clearance by more than 90%. I mean, how is that physically possible?
Fluvoxamine is a classic example of competitive enzyme inhibition. So going back to our analogy of the CYP1A2 enzyme as a molecular machine or like a lock, fluvoxamine physically binds to the exact same enzyme that caffeine needs, but it binds incredibly tightly.
Like a broken key.
Right, it acts exactly like a broken key snapped off inside a lock.
So the golden caffeine particles arrive at the liver toll booth, ready to be processed, but every single lane is completely blocked by this medication.
Precisely. The enzyme is jammed, so the caffeine just has to keep circulating in the blood. Fluvoxamine inhibits the enzyme so severely that the elimination half-life of caffeine increases more than tenfold. It jumps from a baseline of roughly 5 hours to a staggering 56 hours.
That is mind-blowing. Wait, if I'm taking fluvoxamine, my liver's toll booth is basically closed for business. That means that one morning cup of coffee I had on Monday is still stuck circling the highway of my bloodstream on Wednesday.
That is exactly what it means. It continues to pulse through your vascular system, completely unable to be broken down into its subsequent metabolites. And as it races through the bloodstream, whether you're clearing it in 3 hours or 50 hours, its ultimate destination, the place where it exerts its most famous highly desired effects, is a heavily guarded biological fortress.
The brain. We've ridden the river of blood all the way up the neck, and we have reached the blood-brain barrier. Now, for anyone unfamiliar, this barrier is famously selective. It's this highly evolved network of tightly packed endothelial cells and astrocytes designed to keep toxins, pathogens, and unwanted chemicals out of the fragile neural landscape. Most things in your blood simply bounce off it.
Right, it's evolved.
But caffeine just glides right through like it isn't even there.
It does, and it achieves this through two distinct mechanisms. First, the blood-brain barrier is fundamentally a lipid membrane. It's a layer of fat. Because the caffeine molecule is remarkably both water-soluble, so it can travel in the blood, and lipid-soluble, it can dissolve right into that fat layer.
So it just melts through.
Yeah, it enters the brain via simple diffusion. It basically slips like a ghost right through the cell membrane.
That doesn't even need a door. It just walks through the walls.
Exactly. But that isn't its only method of entry. It also utilizes what is known as a saturable carrier-mediated transport system.
Meaning there is a specific door, and caffeine somehow has the VIP pass to use it.
Exactly. The brain has specialized transport channels built into the barrier that are designed to actively pull crucial nutrients out of the blood and into the brain. The existence of this specific carrier pathway being used by caffeine suggests that caffeine's molecular structure is remarkably similar to the natural macromolecules the brain actually wants to import, specifically purines.
So it's in disguise.
Yeah, it essentially hijacks an existing transport channel.
But because caffeine uses this specific pathway, if you have high levels of caffeine in your blood, it creates a bottleneck. The sources note it can cause a dose-dependent inhibition of adenine transport across the barrier.
Think of it like a revolving door at an office building. If 1,000 golden caffeine particles are rushing through the revolving door all at once, then naturally occurring adenine molecules, which, by the way, your brain desperately needs for energy metabolism and DNA synthesis, they can't get into the building. Caffeine is clogging the channel. Yeah, and researchers note this effect could be particularly critical during the neonatal period, which is when this carrier-mediated adenine transport is believed to be operating at its maximum essential level for brain development.
Okay, here's where it gets really interesting. Because once those golden caffeine particles breach the fortress, slip past the barrier, and enter the brain itself, they do something completely counterintuitive, something that feels entirely backward.
Oh, the vascular response.
Yes. When you drink coffee, you feel a rush, you feel energized. You would logically think a stimulant would rush more blood to the brain to wake it up, but it doesn't.
No, it does the exact opposite. Caffeine acts as a potent vasoconstrictor in the central nervous system. As it enters the brain, it stimulates specific medullary, vagal, vasomotor, and respiratory centers in the brainstem. Furthermore, it directly blocks adenosine receptors on the smooth muscle tissue that actually lines the cerebral blood vessels.
Smooth muscle tissue. So the blood vessels themselves are wrapped in muscle, and caffeine tells that muscle to flex.
Yes. It causes the cerebral arteries and veins to physically constrict, narrowing their diameter significantly. Think of pinching a garden hose.
Okay.
The immediate result is a pronounced, measurable decrease in overall cerebral blood flow, or CBF.
And it doesn't even happen evenly across the brain, does it? The functional MRI data shows that the anterior regions of the brain, specifically areas like the dorsolateral prefrontal cortex, which handles executive function and decision-making, experience a faster and more profound rate of blood flow decline than the posterior regions.
Yes.
So the very front of your brain, the part doing the most complex thinking, is losing blood faster than the back.
Which is an astonishing physiological response when you consider the sharp mental clarity we universally associate with a cup of coffee.
Yeah.
You're experiencing elevated cognition while simultaneously choking off the brain's blood supply.
Exactly. This is the vascular paradox. If the caffeine is physically restricting blood flow to my prefrontal cortex, shouldn't I feel faint? Shouldn't I be dizzy and slower? How am I sitting at my desk, hammering out emails, feeling more alert when my brain is literally receiving less blood?
It seems impossible until we look at the compensatory mechanisms of brain metabolism. Despite this pronounced, chemically induced drop in blood supply, the brain's overall cerebral metabolic rate of oxygen, the CMRO2, does not change.
Meaning the brain still demands the exact same amount of oxygen to keep the lights on and the neurons firing. It refuses to power down.
Right. So it faces a crisis. It needs the same amount of oxygen, but it's receiving less blood. To survive and maintain function, the brain significantly elevates its oxygen extraction fraction, or OEF.
Oxygen extraction fraction. Let's break that down for the listener with an analogy.
Sure. Imagine a train rolling through a station. The train is the blood, and the passengers are the oxygen molecules. Normally, the train moves quickly, and only a few passengers have time to jump off onto the platform, which is the brain tissue. But caffeine has pinched the blood vessels. The blood flow is restricted, meaning the transit time of the blood moving through the brain is now slower.
The train has been forced to slow down to a crawl as it moves through the station?
Precisely. Because the blood is moving slower, the brain tissue has more time to pull oxygen out of it. It elevates its extraction fraction. It pulls a much higher percentage of oxygen out of the limited blood that is available. It compensates perfectly, ensuring the metabolic rate never drops.
So the feeling of alertness we get isn't coming from a rush of fresh blood. It's happening purely on the chemical level, independent of the vascular system. We are zooming in again in our theater of the mind here. We're moving past the constricted blood vessels, past the endothelial cells, right down to the billions of individual neurons forming these glowing, three-dimensional networks in the dark. Synapses are firing like electric stars across a cosmic void. We have arrived at the site of the great neurochemical battle.
And every battle needs an antagonist. In this biological narrative, the antagonist to alertness is a naturally occurring molecule called adenosine.
Let's visualize adenosine. If our caffeine is glowing golden particles, let's picture the adenosine as soft blue particles.
A perfect countervisual. And to understand the battle, you have to understand where these soft blue particles come from. Adenosine isn't something your body just secretes randomly. It is a direct byproduct of cellular energy use.
It's exhaust.
Exactly. Your cells run on a molecule called ATP adenosine triphosphate. Every time a neuron fires, every time you think a thought, move a muscle, or process an emotion, you're burning ATP. And when ATP is burned for fuel, it breaks down, and the leftover pieces form adenosine.
I see.
Therefore, under normal conditions, the longer you're awake and active, the more of these soft blue particles naturally accumulate in your brain tissue.
They are the biological ledger of how much energy you've spent since you woke up. And as these blue particles accumulate, they don't just float around, they have a specific job. They seek out and attach to specific docking stations on the neurons, right? Primarily the A1 and A2A receptors.
And when a blue adenosine particle locks into one of those receptors, it triggers a cascade that suppresses central nervous system activity. It acts as a primary sleepiness signal.
So it slows things down.
It decreases the release of excitatory neurotransmitters. It physically alters the electrical potential of the neuron, making it slower, heavier, and just less likely to fire. As more and more blue particles dock, the electrostars in our visual start to dim. The network powers down. This is the mounting pressure of fatigue you feel at 10:0 p.m.
But then, the golden caffeine structures arrive. Having survived the liver, crossed the blood-brain barrier, and slowed the blood flow, they flood into the neural landscape. And as we mentioned earlier regarding the transport channels, caffeine has a three-dimensional chemical shape that is an almost identical match to adenosine.
It's a molecular doppelganger?
Right. So the golden particles fit perfectly into the adenosine receptors, like fake keys sliding effortlessly into locks.
But importantly, they don't turn the lock.
They're competitive antagonists.
Correct. In pharmacology, an agonist activates a receptor, while an antagonist simply blocks it. Caffeine binds to the A1 and A2A receptors with extremely high affinity, but it lacks the necessary structural components to actually trigger the intracellular sleepiness signal.
It just sits there.
Exactly, it just physically occupies the space, effectively blocking the soft blue particles from getting in.
It's a microscopic, highly aggressive game of molecular musical chairs. The music stops, and the golden caffeine particles steal all the available seats. They sit down, leaving the mounting swarm of blue adenosine particles wandering around the neural void with absolutely nowhere to sit. The exhaust is still building up, but the brain can no longer feel it.
That is precisely what is happening. And while this blockade happens throughout the brain, it's particularly impactful at the A2A receptors in a deeply embedded, ancient region of the brainstem called the ventrolateral preoptic area, or VLPO.
But wait, I have to push back here. If caffeine is just a blocker, if all it does is sit in a chair and stubbornly prevent a sleep signal from firing, where does the actual energy come from? When I drink an espresso, I don't just feel not sleepy, I feel physically energized. My heart rate ticks up, my thoughts race. How does a passive blocker create an active feeling of energy?
It's a profound realization to understand that caffeine itself does not give you energy. It contains 0 calories. It has no biological fuel that your brain can burn for power. All it does is take the brakes off a system that is desperate to run.
The brain is trying to hit the brakes, and caffeine cuts the brake line.
Exactly. Let's look at the mechanics of that. By blocking those A2A receptors in the VLPO, caffeine indirectly reduces inhibitory GABA neurotransmission. Now, GABA is the brain's main inhibitory signal. Normally, the VLPO sends GABA to another region called the tuberomammillary nucleus to shut it down for sleep.
The tuberomammillary nucleus. I know we're throwing a lot of anatomy out there, but let's explain what that center actually does when it's not being shut down.
It is a critical histaminergic projection nucleus. It's the sole source of histamine in the central nervous system, and its primary job is to promote intense wakefulness and arousal.
Okay.
Under normal evening conditions, the accumulating adenosine tells the VLPO to release GABA, which puts the brakes on the tuberomammillary nucleus, allowing you to sleep.
But the golden particles have blocked the adenosine, so the VLPO never gets the message to release the GABA brakes.
Precisely. By disinhibiting this nucleus, caffeine takes the sleepiness, breaks off the entire brain. It allows the central nervous system's endogenous stimulants, your own natural excitatory neurochemicals like glutamate, histamine, and adrenaline, to run entirely unchecked.
So the neural network lights up like a sprawling city at night. The power plant was always running. Caffeine just stopped the city managers from flipping the switch to turn the lights off.
That is the perfect analogy. You're feeling your own raw, uninhibited neurochemistry. And when those lights come blazing back on, specific districts of the neural city shine much brighter than others.
Let's zoom in on those specific districts. The prefrontal cortex, which we noted earlier is receiving less blood, paradoxically becomes noticeably brighter in its electrical activity. This represents the sharp increase in executive focus, planning, and alertness. But there's another crucial player lighting up in the center of the brain: dopamine.
Ah, yes. Dopamine is the neurotransmitter most heavily associated with motivation, reward, and the drive to pursue goals. Now, caffeine doesn't directly bind to dopamine receptors. It isn't a direct dopaminergic agonist like certain illicit stimulants,
Right.
but it massively influences the dopamine system through a fascinating structural quirk in the brain. Adenosine receptors and dopamine receptors often physically link together to form unified complexes called heteromers.
They are physically tethered together in an area called the striatum.
Correct. A heteromer is basically a fancy way of saying two completely different receptors physically grab onto each other and lock together in the cell membrane to form a single functioning unit. What happens to one instantly and physically alters the shape of the other. The key complexes here are the A1D1 heterodimer and the A2A-D2 heterotemer.
It's like two people tied together in a three-legged race.
Under normal non-caffeinated conditions, when the soft blue adenosine particle binds to its half of the complex, the entire structure shifts. The adenosine receptor actually reaches over and allosterically modulates the dopamine receptor. It physically contorts the shape of the dopamine receptor, decreasing dopamine's ability to bind and work effectively.
The blue particle sits down, pulls on the tether, and essentially yanks the chair away from dopamine. It dampens your motivation to do anything.
Exactly. But when the golden caffeine particle arrives and blocks the adenosine receptor, it prevents that structural contortion. It prevents the interference. By sitting in the A2A chair, caffeine enhances dopamine's ability to easily bind to and activate its own D2 receptors.
It holds the chair steady so dopamine can sit down. And this is what creates that specific 9:15 a.m. feeling. You get to the office, You drink your coffee, and suddenly, tackling your overflowing inbox doesn't seem so bad. It creates a subtle sense of motivation, reward, and well-being.
And it actually goes one step further. Caffeine also promotes the release of more dopamine into the synapses. By blocking A1 receptors on dopaminergic neurons, it releases the presynaptic brake, allowing a larger flood of dopamine to pour into the dorsal striatum and the nucleus accumbens core.
So it makes the dopamine receptors more receptive, and it pumps more dopamine into the system to take advantage of them. This rush of unchecked neural activity translates into highly measurable cognitive impacts. When researchers look at the data, the most consistent, undisputed, proven benefit of caffeine is an increase in cognitive velocity. Your reaction time drops. You physically process incoming visual and auditory stimuli and react to them faster.
But there is a very important catch that the sources outline. We see a distinct reaction time versus accuracy trade-off.
More speed isn't always better.
Right. It's a dose-dependent curve. At low to moderate doses, say 1 to 2 cups of coffee, both your reaction time and your accuracy improve. You're faster and you're sharp. But as you continue to increase the dose, pushing more and more caffeine into the system, while your response times will continue to drop, making you physically faster and faster, you eventually hit an intake threshold where that sheer speed comes at the heavy cost of decreased accuracy.
You become fast but sloppy. Your brain is firing so quickly that it stops verifying the information. And this brings us to the topic of memory, which I think is a massive point of confusion for the general public. For decades, students have chugged coffee or energy drinks to help them study. I know I did in college. I thought the golden particles were locking the facts into my brain. But the research we're reviewing calls this the illusion of memory enhancement.
It is a pervasive myth. If we look closely at the rigorous cognitive literature, caffeine generally does not improve the active encoding or learning of new, complex material. When you are sitting down, reading a textbook, and intentionally trying to memorize new facts, caffeine does not fundamentally alter your brain's medial temporal lobe or hippocampus to make that encoding process more efficient.
Wait, so all those nights I chugged coffee while cramming for a chemistry test didn't actually help my brain learn the chemical bonds?
Not directly, no. It helped you stay awake to look at the textbook longer. It prevented the adenosine from shutting your eyes. It improved your selective and sustained attention, meaning you were less easily distracted by your phone. It increased your baseline arousal. But it didn't chemically enhance the actual neuronal encoding of that intentional learning.
That is wild.
In many cognitive testing scenarios, what looks like better memory on a spreadsheet is often just the test subject reacting to the multiple choice questions faster because of that cognitive velocity we just discussed.
It's the illusion of being smarter, when really you're just clicking the mouse quicker. But reading the stack of sources, there is one very specific, very fascinating exception regarding memory. And it's not about encoding the memory in the moment, it's about memory consolidation. This is the Johns Hopkins University study.
Yes, and the timing of the dose is the critical defining factor here. The researchers at Johns Hopkins set up this elegant study to look at a specific cognitive function called pattern separation.
Pattern separation, this is the brain's ability to make difficult visual or mental discriminations between highly similar but not identical items.
Exactly. It's not just recognizing a picture of a wicker basket. It's looking at a wicker basket the next day and knowing, no, that's a slightly different wicker basket than the one I saw yesterday. The handle is thicker. That requires incredibly precise memory retrieval.
So how did they test it with caffeine?
They had participants study a large series of images. But crucially, they did not give them caffeine beforehand. They let them study the images in their natural baseline state. Then, immediately after the study session concluded, they gave the participants a 200 milligram caffeine tablet, which is roughly the equivalent of a strong 12-ounce cup of coffee.
So the golden particles enter the brain after the information is already in there?
Right. When the researchers brought the participants back 24 hours later and tested them, the group that received the post-study caffeine was significantly better at distinguishing the original images from closely matched, tricky, similar images than the placebo group.
So it didn't help them learn it in the moment, it helped their brain chemically lock it in afterward. It fortified the long-term memory consolidation process overnight, making the memories more resilient and resistant to forgetting.
That is the current scientific consensus. The acute cognitive benefits of caffeine are restricted to sustained attention, reaction speed, and, if timed correctly post-learning, pattern separation. But the story of these golden molecules doesn't end with a temporary boost in focus. because the human brain is a highly adaptive, deeply stubborn system.
And it does not like having its brakes cut. Which brings us to the dark side of this daily ritual: tolerance, withdrawal, and anxiety.
The central nervous system seeks homeostasis above all else. It wants balance. It wants the lights to dim when energy is spent. So when you constantly, day after day, flood your brain with golden caffeine particles that stubbornly block all the adenosine receptors, the brain realizes it has lost control of its own sleep signals.
It senses that the VLPO is being suppressed.
Right, so it fights back through a biological process called neuroadaptation.
It essentially looks at the musical chairs game and says, fine, if you're gonna block all my chairs with golden particles, I'll just build more chairs.
Precisely. The brain begins to physically synthesize and express a higher number of A1 and A2A adenosine receptors in its arousal and motivation circuits. It physically alters its own structural anatomy to accommodate the chronic presence of the drug.
It grows more receptors. So now you have a massive surplus of chairs, which means your standard morning cup of coffee no longer has enough golden particles to block them all. Some of the blue adenosine particles find the new chairs, and you feel tired again. You have developed a physiological tolerance. You need progressively larger amounts of caffeine to achieve the exact same energizing effect.
And the research shows this physical dependence happens incredibly fast. It can develop in individuals consuming little more than 100 milligrams a day. That's a single standard mug of coffee. If you drink 1 cup a day, every day, your brain has likely altered its receptor density.
And this permanent structural change in the brain leads to a devastating concept called the withdrawal reversal hypothesis. I want to walk through this slowly because it completely recontextualized my entire relationship with my morning routine.
It's a hard truth for habitual coffee drinkers to accept.
So, because you have physically grown more receptors, when you go to sleep at night, you obviously stop drinking coffee, you undergo overnight abstinence. Your liver, regardless of how fast or slow it is, spends the night clearing the golden particles out of the brain.
By morning, the blockade is lifted. But now, you don't just have your normal amount of receptors. You have the excess upregulated receptors, and they're completely unblocked, sitting empty.
And waiting for them is the natural adenosine that has been slowly accumulating during the early waking hours, or that just wasn't fully cleared during a restless sleep. It's an avalanche of soft blue particles.
Yes. Because there are so many open receptors, this sudden surge of adenosine overwhelmingly binds to the neural network. It floods the brain with massive, uninhibited signals promoting intense fatigue, a depressed mood, localized difficulty concentrating, and generalized sluggishness. You're experiencing acute drug withdrawal.
So at 7 a.m., when you stumble into the kitchen, pour that fresh cup, drink it, and feel that glorious, warm rush of alertness, that feeling of, I am finally awake and ready for the day.
You are not elevating your cognitive performance above a normal natural baseline. You are merely reversing the severe sluggishness of the acute withdrawal state you entered overnight.
Wow.
The intense boost you feel is largely an illusion. You're simply treating a mild chemical addiction to get your brain back to zero.
So my entire morning personality, the energetic, ready-to-work guy, is just me medicating a micro-addiction to reach a baseline that someone who doesn't drink coffee just wakes up with naturally.
From a strict neuropharmacological perspective, yes. Habitual users operate from a chronically lowered arousal baseline. Your normal is artificially depressed by the extra receptors.
And if you try to cheat the system, if you try to push past that tolerance by consuming massive amounts of the golden particles to force the brain back into overdrive, you run into severe adverse physiological effects.
At that point, you're dealing with caffeine intoxication. It isn't just a descriptive term, it's a formal clinical diagnosis recognized in the DSM-5. When the golden particles absolutely overwhelm the central nervous system, typically when an individual ingests over 400 to 500 milligrams in a very short single time frame, the system goes into toxic overstimulation.
What does that actually look like in the body?
The amygdala, the brain's fear and threat detection center, hyperactivates. The symptoms cascade rapidly. Severe internal restlessness and inability to sit still, psychomotor agitation, muscle twitching, and severe gastrointestinal disturbance as the smooth muscle in the gut goes into overdrive.
And crucially, it heavily affects the cardiovascular system.
Right. High doses, especially from modern energy drinks that can deliver 320 milligrams or more in a single rapidly consumed can, act as antagonists at the specific adenosine A1 receptors located in the tissue of the heart.
Because the heart has its own adenosine receptors.
It does. And in the heart, adenosine normally acts to slow the electrical conduction through the AV node. It's a natural pacemaker, keeping the heart rhythm steady. When massive amounts of caffeine block those receptors, you remove the inhibitory signals. The result is tachycardia, an abnormally, sometimes dangerously fast resting heart rate, and intense heart palpitations.
It's terrifying, but even if you never reach intoxication, even if you just decide, you know what, I'm done, I'm quitting coffee cold turkey tomorrow to get rid of these extra receptors, the withdrawal process itself is violently jarring. It's not just mood disturbances and yawning. You get severe, debilitating withdrawal headaches. And understanding why you get the headache brings us back to the blood vessels.
Exactly. Remember the vascular paradox. Caffeine acts as a vasoconstrictor in the brain, keeping the cerebral blood vessels tight and narrowed, reducing blood flow while the brain extracts more oxygen.
Right, the pinched garden hose.
When you abruptly stop consuming caffeine, that chemical clamp is suddenly removed. The smooth muscle relaxes. Those cerebral blood vessels rapidly dilate. They widen out significantly, leading to a sudden, rushing increase in blood volume and vascular pressure flooding back into the brain cavity. The brain is encased in a rigid skull. It doesn't like sudden pressure changes.
Ouch.
Yeah, that rapid vascular shift manifests as a deep, pounding, throbbing headache that can last for days until the vessels adapt to the new normal.
And incredibly, the sources point out another cruel symptom of withdrawal, which is paradoxical insomnia. You are exhausted, your brain is absolutely flooded with blue adenosine sleep signals binding to millions of extra receptors. You feel like you haven't slept in years, but you lay in bed and you cannot fall asleep.
It feels like a biological cruel joke, but the sources explain this as a circadian rhythm disruption. Your body's master biological clock, located in the suprachiasmatic nucleus, has had its natural rhythms artificially altered by years of caffeine dependence.
Right.
When you remove the drug, the neurochemical timing of melatonin release and cortisol production is completely out of sync with your new adenosine levels. The systems are fighting each other, struggling to recalibrate to a natural baseline.
It is a complex, painful, physiological unraveling. But as bleak as the withdrawal reversal hypothesis sounds, we have to balance this dark side with the long-term, decades-long realities of chronic use. Because this is where the story pivots one last time.
Yes, because despite the daily withdrawal loop, despite the physiological adaptations and the frustrating baseline illusion, chronic, lifelong use of caffeine actually reveals profound, disease-modifying biological benefits. The data strongly forces us to shift our tone back to awe and discovery.
Because the long game of coffee consumption is actually keeping our brains intact, if we look at the vast pools of epidemiological data following hundreds of thousands of people over decades, we see incredibly strong links between regular caffeine use and profound neuroprotection. We're talking about moderate sustained use, roughly 3 cups a day over a lifetime. That specific level of consumption is associated with a massively reduced risk of developing severe neurodegenerative conditions, specifically Parkinson's disease and Alzheimer's disease.
The correlation of the data is undeniable, but it's the mechanisms behind this protection that are truly mind-blowing. It goes far beyond just blocking sleepiness. Let's look at the first primary mechanism.
Autophagy.
Autophagy. Auto meaning self, phagy meaning eating. The cells are eating themselves. This is the brain's internal cellular housekeeping system. Exactly. To understand why this matters, you have to understand the pathology of these diseases. Parkinson's disease is, at its core, a protein misfolding disease. Inside your neurons, abnormal proteins, specifically a highly toxic mutant variant called alpha-synuclein, begin to misfold. Because they are the wrong shape, they aggregate. They clump together into dense, toxic masses called Lewy bodies, which slowly suffocate and destroy the dopamine-producing neurons in the substantia nigra.
And autophagy is the process by which the healthy cell identifies these toxic clumps and destroys them before they can cause damage.
Right, it's an intracellular degradation system. The cell encapsulates the misfolded proteins and delivers them to the lysosomes, which is like the stomach of the cell to be broken down and recycled into raw materials.
It's like a fleet of microscopic nocturnal street sweepers coming out to clean up the biochemical trash from the city's streets so traffic can flow the next day.
A perfect visual. And what the latest neurobiology research demonstrates is that caffeine acts as a highly potent trigger for this deep cleaning process. It significantly enhances autophagic flux. Specifically, it regulates macroautophagy and a highly targeted process called chaperone-mediated autophagy, or CMA.
Chaperone-mediated autophagy, so it's sending specific guards to escort the toxic trash out.
Yes. Studies using the alpha-synuclein fibril model of Parkinson's, where researchers intentionally induced these toxic clumps in living neural networks, found that chronic caffeine treatment actively attenuated the resulting microglial activation and neuroinflammation. It aggressively helped the cells clear out the toxic mutant proteins.
I just want to pause and marvel at the sheer poetry of that. Think about where we started. A chemical that evolved millions of years ago as a botanical scorched earth pesticide designed to paralyze the nervous systems of predatory beetles is somehow perfectly shaped to trigger the deep cleaning, life-saving autophagic mechanisms of human brain cells to stave off our most devastating neurodegenerative diseases.
It is a profound, almost unbelievable biological crossover. And the systemic protection doesn't just happen in the brain tissue itself. It brings us to the second protective mechanism, which requires us to look back at the digestive tract, the gut-brain axis.
We established earlier that when you drink that cup, the golden particles are rapidly absorbed in the small intestine. But it's not a 100% efficient process. What's left over, the unabsorbed fraction of the coffee and the caffeine, continues moving down the digestive tract and enters the colon, where it meets the gut microbiota, the trillions of bacteria living in your large intestine.
And those bacteria don't just ignore it. The gut microbiota actually actively ferments the remaining caffeine and coffee compounds. This metabolic process has a profound shaping effect on the ecology of your gut. Long-term, daily coffee intake significantly alters the microbial composition, promoting the growth of highly beneficial bacterial strains.
And we now understand, through recent revolutions in gastroenterology, that the gut microbiome isn't just a digestion center. It communicates intimately, constantly, with the brain's central neuroimmune system via the vagus nerve and the production of short-chain fatty acids.
It is a massive bidirectional communication highway. By altering the bacterial flora in the colon, caffeine is reducing systemic inflammation and indirectly influencing brain health and maintaining neural homeostasis from the bottom up. It is protecting the brain from the gut.
But the sources also make a crucial point. This profound neuroprotection isn't uniform for everyone. You can't just prescribe 3 cups of coffee to everyone and guarantee they won't get Parkinson's. There are genetic modifiers at play that dictate how your specific biology interacts with the golden particles. The sources specifically highlight variations in 2 genes, GRAN2A and LRRK2.
This data raises a vital point about the future of personalized medicine and pharmacogenomics. A massive case control study analyzed the DNA of Parkinson's patients versus healthy controls. They found that for individuals carrying a very specific high-risk genetic variant in the LRRK2 gene, regular caffeine intake didn't just slightly reduce their risk. It significantly reduced their risk of developing Parkinson's by an incredible 15-fold.
15-fold, that is an exponential, massive shield against the disease.
But only for that specific genetic profile. For others, the protection is moderate. The way your individual genome is constructed fundamentally alters how the pesticide interacts with your cellular cleanup crews.
So when we look at the totality of what we've unpacked, caffeine's true ultimate power might not be the acute cognitive buzz we crave every morning at 9:19 a.m. That feeling is just the short-term trick. The real magic, the true biological miracle of the golden molecule, is the silent, decades-long maintenance of our neural infrastructure.
That is the grand synthesis of the data. As a species, we willingly endure the daily withdrawal loop, the mild addiction, and the altered baseline arousal in exchange for profound, long-term neuroprotection and structural cellular health.
What a journey. We started with botanical warfare, looking at how the coffee plant poisons its own soil to protect itself from competitors and insects. We tracked those golden molecules down the esophagus, watching them survive the highly variable metabolic toll booth of the liver's CYP1A2 enzyme.
Right.
We watched them miraculously glide through the lipid walls of the blood-brain barrier, pinching the cerebral blood vessels closed while the brain desperately extracted more oxygen to compensate for the slower transit time. We witnessed the aggressive game of molecular musical chairs, where the golden caffeine keys steal the seats from the soft blue adenosine molecules, indirectly cutting the GABA brakes on the central nervous system, unleashing a flood of dopamine and sparking measurable cognitive velocity.
It's quite the resume.
And ultimately, we saw how chronic daily exposure to this botanical pesticide triggers the brain's internal street sweepers, clearing out toxic proteins and communicating with the gut microbiome to protect our minds as we age.
It's arguably the most remarkable, naturally occurring compound on Earth, purely because of how deeply and permanently it has integrated itself into global human physiology. But if we connect all of this biological data to the broader scope of human history, It leaves us with a deeply provocative thought that goes far beyond medicine.
What's that?
We established that chronic caffeine consumption physically alters the structure of the human brain, the neuroadaptation we discussed. It forces the brain to grow millions of new adenosine receptors to compensate for the daily blockade. It fundamentally alters our baseline state of arousal, our biological sleep pressure, and our cognitive velocity.
Right. It changes the physical hardware of the brain.
Now, zoom out from the individual and look at the species. Consider that over 80% of the adult population globally consumes caffeine every single day. Millions of tons of these processed seeds are ingested annually. The vast majority of humanity is walking around with brains that have structurally adapted to the constant daily presence of this plant alkaloid.
Okay, I see where you're going with this.
If this molecule fundamentally increases cognitive velocity, sustains focused attention past the point of natural fatigue, and chemically overrides our circadian biology to allow us to work long past natural sunset. Did the mass global adoption of coffee actually spark the modern world?
Oh, wow.
Think about it. Before the widespread trade of coffee and tea, European populations largely drank weak beer throughout the day because the water wasn't safe. The baseline of human consciousness was essentially a mild depressant haze dictated strictly by the rising and setting of the sun. Then suddenly an entire civilization switches to a potent neural stimulant that blocks adenosine and allows for sustained, focused, abstract thought for 16 hours a day.
Are you suggesting that the Industrial Revolution, modern capitalism, the concept of the 8-hour shift, and the massive leaps in technological innovation over the last few centuries were fundamentally catalyzed by this specific botanical pesticide?
I am suggesting that modern human productivity, as we define it today, is biologically unnatural. The labor systems we've built are entirely dependent on chemically overriding our natural sleep cycles. What would human history, culture, and cognitive achievement look like if we had never discovered this golden molecule? Are we currently experiencing true baseline human nature, or is the entirety of modern society simply human nature heavily modified by coffee Arabica?
That is an immense concept to process. The idea that our entire civilization's collective mental baseline and economic structure is artificially propped up by a plant's chemical defense mechanism. It's not just a morning drink, it's the foundational operating system of the modern world.
It is certainly something to ponder during your next morning brew.
I will absolutely never look at a coffee shop the same way again. Thank you so much for joining us on this deep dive. Next time you sit at your desk and hold that warm cup of dark liquid, picture those golden particles, think about the incredible, violent, miraculous biological journey they're about to take, and ask yourself, who is really in control? Until next time.